Welcome to the world of semiconductors. Here's a question to get your brain buzzing. What do SAN and high-tech gadgets have in common? Surprisingly, both involve silicon, one of the most important materials in electronics. Today, we begin with intrinsic semiconductors, also called pure semiconductors. Think of them like innocent bystanders in the material world with no impurities or doping. An intrinsic semiconductor is a completely pure substance where the number of negative charge carriers, electrons, is exactly equal to the number of positive charge carriers, holes. Imagine a big, evenly seated classroom where every student has their own desk. That's how each atom contributes just one valence electron to perfectly bond with neighboring atoms in a crystal lattice. This bonding results in a neat, orderly structure. Silicon and germanium are the frontrunners for pure semiconductors. Why? Because they each have 4 valence electrons, just enough to bond with 4 neighbors and create a rock-solid crystal structure. Now here's the twist. At absolute zero, which is 0 Kelvin, all electrons are happily sitting in the valence band. No one's partying in the conduction band, so the material behaves like an insulator. But as temperature rises, some electrons get enough energy to break free and leap into the conduction band, and that's when current begins to flow. The energy needed for this jump is called the band gap, denoted as E sub J, which stands for band gap energy. It's like the energy needed to get out of bed on a Monday morning, and trust me, it's not always easy. Ready to explore how all this shows up in energy band diagrams? Let's move on. Alright, imagine an energy level structure with 2 bands, the valence band below and the conduction band above. Between them lies the forbidden zone called the band gap. At normal room temperature, not everyone has the energy to be excited, but some electrons do. When these brave ones gain enough thermal energy, they jump from the valence band up into the conduction band. This leaves behind a vacancy, which we call a hole, in the valence band. Now both the electron in the conduction band and the hole in the valence band can participate in conducting electricity. For silicon, this required energy, the band gap, is about 1.1 electron volts. For germanium, it's a bit lower, around 0.7 electron volts. A smaller band gap means more electrons can jump at the same temperature. And watch this carefully, as temperature goes up, the number of electron-hole pairs increases exponentially. That's right, the hotter it gets, the more carriers are generated. Ultimately, the electrical conductivity, we denote it by sigma, depends on both the number of electrons and the number of holes, because in intrinsic materials, both kinds of carriers matter equally. Up next, we'll talk about just how many carriers exist, that is, the carrier concentration. Let's dive into that. Okay, now let's talk numbers, specifically carrier concentration. In an intrinsic semiconductor, this concentration is denoted as in sub I, which tells us the number of free electrons or holes per unit volume. Since it's a pure material, every time one electron jumps into the conduction band, it leaves a hole behind, so the number of electrons, N, is always equal to the number of holes, P. That means N equals P equals N sub I. The key thing to remember is N sub I increases very quickly with temperature. Why? Because more electrons gain thermal energy to overcome the band gap and jump into the conduction band. And here's how we represent this relationship mathematically. N sub I equals capital A times T to the power 3 by 2 multiplied by exponential of negative E sub G divided by 2 kT. Let me spell that out. N sub I equals a multiplied by T raised to 3 halves times E raised to the power negative E sub G divided by 2 kT. Here, A is a material-dependent constant, T is the temperature in Kelvin, E sub g is the band gap energy in electron volts, and K is Boltzmann's constant. A key insight: materials with a larger band gap are less sensitive to temperature. They generate fewer carriers unless the heat is really cranked up. So the kind of material and the temperature both decide how many carriers you get. Next, we'll see how all this impacts conductivity. Now that we've got electrons and holes moving around, let's talk about what really matters in a circuit: conductivity. In intrinsic semiconductors, both electrons and holes contribute to conduction when an electric field is applied. Think of a two-lane road, one for electrons moving in one direction and one for holes drifting the other way. Together, they make traffic flow smooth. The total electrical conductivity, represented by sigma, is given by the expression sigma equals E times N sub I times, open bracket, nu sub E plus nu sub H, close bracket. In words, that's sigma equals electronic charge E multiplied by intrinsic carrier concentration N sub I multiplied by the sum of electron mobility mu sub E and hole mobility mu sub H. Here, mobility is defined as the drift velocity of a carrier per unit electric field. So we say mobility mu equals drift velocity divided by electric field. Since in pure semiconductors, N equals P, both carriers contribute equally to the conduction. Now here's a fun conflict. With rising temperature, more charge carriers are generated, increasing N sub I. But the mobility mu tends to go down due to increased scattering of the carriers with vibrating atoms. So in the end, the net effect on conductivity depends on which factor dominates, more carriers or slower mobility. Next, we'll revisit the energy bands one more time as temperature rises. Let's connect it back to physical behavior. Okay, back to that energy band diagram, but this time, let's heat things up. Literally. As temperature increases, more and more electrons acquire enough energy, greater than or equal to the band gap E sub g, to jump up from the valence band into the conduction band. That creates free electrons in the conduction band and corresponding holes in the valence band. So picture this: as the temperature rises, dots representing electrons begin to swarm into the upper band, while little holes are left behind below. In an electric field, electrons move toward the positive terminal while holes drift toward the negative terminal, but both movements add up constructively to create current. If you look at the band structure in our diagram, you'll see the valence band at the bottom, the conduction band at the top, and the band gap in between. Right in the middle lies the Fermi level, the average energy level where the probability of finding an electron is 50%. In an intrinsic semiconductor, this Fermi energy, denoted as E sub F, sits roughly midway between the conduction and valence bands. It's symmetrical because there's no doping or imbalance in carriers. It's that perfect balance that makes intrinsic materials such great starting points for understanding semiconductors. Finally, let's summarize everything we've learned so far. Time for a quick review. First, we learned that in an intrinsic semiconductor, the number of electrons is equal to the number of holes, and both contribute equally to conduction. The carrier concentration N sub I increases quickly with temperature and is given by N sub I equals capital A times T to the power 3 by 2 times E raised to the power negative E sub G divided by 2 kT, where E sub G is the band gap energy, T is temperature, and K is Boltzmann constant. Next, total conductivity sigma is calculated using the formula sigma equals E times N sub I multiplied by the sum of mobility of electrons and holes. Band gap energy plays a major role. Silicon has a gap of about 1.1 electron volts, while for germanium, it's about 0.7 electron volts. We found that although increased temperature boosts carrier generation, mobility decreases due to more atomic vibrations, so there's a tug of war determining overall conductivity. Most importantly, intrinsic semiconductors are pure, symmetric, and conduct due to the beautiful thermal creation of equal electron-hole pairs, a phenomenon that lies at the heart of modern electronics. So next time you tap your smartphone, just remember, even pure materials can be powerful when physics is on their side. That's it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.